in the second tutorial of biostatistics, I'll be talking about frequency table. Frequency table is a statistical table which shows the values of variables arranged in the order of magnitude either individually or in groups, and also the corresponding frequency side by side. Frequency table has two main components, that is class and frequency. Class and frequency are the two main components of a frequency table. Now let's see what a frequency distribution is. The frequency distribution is of two types: simple frequency distribution and grouped frequency distribution. In simple frequency distribution, the values of the variables are shown individually, and in grouped frequency distribution, the values of the variables are shown in groups or intervals. Now let's see. This is a raw data of the fecundity of 45 insects. The example of fecundity of 45 insects, and this is a raw data which we got from 45 insects. This does not have any order: 80, 45, 70, 40, 40, 70, 16. It is simply given, and we have to arrange this raw data into a meaningful data. That is the importance of a table, which have to convert this raw data into a meaningful data which is easily understood. And how to convert a raw data into an ordered data or an arrayed data? Data is arranged either in the ascending order or in the descending order, and usually we arrange the data in the ascending order. When you arrange the this data in the ascending order, we have to find the lowest value of the variable. Here the lowest value is 2. Lowest value is 2, and we have to find how many 2's are there in this raw data. This raw data we can find here 1, 2, then 2 is here. Then if we look into the raw data, there are no other 2 value 2, that is 2 is repeated twice. So we have to convert this raw data into a arrayed data. When you arrange this data, we will write 2, again another value 2, then we have to find the next 3 is there, 4 is there, 5 is there, like that we have to check, and after 2 the next smallest value is 16. Then we write 16 here. How many 16s are there? There are 3 values: 16, 16. Then next to 16 we have to find the number which is next to 16, that is 19. We have to write 19, and that is how we have to convert a raw data into arrayed data. Here you can see the arrayed data of the raw data which is given here. And when we compare this arrayed data is actually a quite tedious and it is time consuming. These two are the drawbacks of this arrayed data, that is, it is tedious and it is time consuming. So if number of observation is very large, it's comparatively it is small. If the number of observation is very large, like 100 values or 1000 values are there, it is very difficult to do each value one by one. Then if the observation is large, tabulation of data with a simple frequency is adopted, that is simple frequency table. Simple frequency table. In simple frequency table, we will divide the table into two parts, that is variable and frequency. Then the first variable, as we have said, the lowest value here is 2. So we will write the variable 2. Then the next variable 16. Then we have to find the next variable 19. It goes on like that. 2. How many times 2 is repeated here? 2 times. So we write frequency. Frequency is how many times the variable 2 is repeated. That is the frequency. So 2. Then how many times 16 is repeated? 1, 2 and 3. So frequency of 16 is 3. Then we have to find how many times 19 is repeated here. 19 we have to check like this. 19 only one time. Then the next variable, if it is, that is 20. After 19 you have 20. We have to check how many times 20 is repeated here. 21, then 2, 3, 4 and 5 and 6 times 20 is repeated here. And so we write the frequency of 20 as 6. And then it goes on, and here you can see how simple frequency table is constructed with this raw data. Then when a large number of observations varying in wide range, this is actually comparatively small data, when a large number of observations varying in a wide range are available, these are classified into several smaller groups according to the size of the values. According to the size of the values, it is divided into smaller groups, and each of these groups is called a class interval or a class. If the data is large, it is grouped, and each group is called a class interval or class. Class interval is a set of numerical data that is grouped into several classes, and the range of each class is known as a class interval. Then coming to class interval, class interval is of two types: continuous class interval and discontinuous class interval. Continuous and discontinuous class interval. With the continuous class interval, we construct a overlapping frequency table, and with the discontinuous class interval, we construct a non-overlapping frequency table. And that I will be discussing later on in this tutorial itself. When we plan to construct a class, the classes must be mutually exclusive class. This means that no data value can fall into two different classes. When you prepare the classes, it should be between 5 and 20 classes, not less than 5 or not even more than 20. The classes must be of equal width. Then that means the class should be like 5 to 10, then 10 to 15, 15 to 20, not like 10 to 15, then 15 to 25. That's wrong. That is, it should be of equal width, and the class must be continuous. There should not be any gaps in a frequency distribution. The classes must be all inclusive, and this means that all data values must be included. Now we will see what a class boundary is. Class boundary. Class boundaries are the numbers that separate classes without forming gaps between them. And the distance from the upper limit of the first class to the lower limit of the second class is the class boundary. For example, in this example, a class if 7 to 18, 19 to 30, then 31 to 42. These are the three classes, and we'll see how we'll write the class boundary for these classes. The class boundaries of this class are the first, that is the classes 7 to 18 and 19 to 30, and the first class boundary is calculated like this, that is the first class to the 19 minus 18, that is the lower limit of the second class and the upper limit of the first class. That is 19 minus 18 is equal to 1. 19 minus 18 is equal to 1, and half this distance is the class boundary, and half of 1 is equal to 0.5. The first class lower boundary. First class lower boundary is equal to, we have to subtract this 0.5 from 7. That is 7 minus 0.5 is equal to 6.5. It is the first class lower boundary. Now we will calculate the first class upper boundary. First class upper boundary. First class upper boundary is equal to 18 plus 0.5. 18 plus 0.5, that is equal to 18.5. This is first class lower boundary is 7 minus half the distance, that is 0.5, and first class upper boundary is 18 plus 0.5. Like that we can find the class boundaries of each class, as you can see here. With the class boundaries, you can modify this table 6.5 to 18.5. Then next 18.5 to 30.5. Then 30.5 to 42.5. And the frequency can be 6, frequency 6, 10, 13, like that. This is how a class boundary is calculated. Then class width. Class width is calculated by subtracting the upper limit or the lower limit of the second class with the lower limit of the upper class. So in this example, 19 minus 7, that is equal to 12. That is the class width. Class width is calculated by subtracting the lower limit of the second class with the lower limit of the first class. So it goes like that. 7 plus 12 is 19. 19 plus 12 is 31. It goes on like that. Then how to find the relative frequency? Relative frequency Relative frequency is the portion or percentage of the data that falls in a particular class. It is a portion or percentage of the data that falls in a particular class. Relative frequency is equal to class frequency divided by sample size. Class frequency divided by sample size, or is equal to F divided by N. Relative frequency is class frequency by sample size, or F divided by N. And in this example, we can calculate the relative frequency by the sample size here is 50. The sample size of this table is 50. So the relative frequency is calculated by the class frequency, that is 6 divided by the sample size, that is 6 divided by 50. Then 10 divided by 50. Then 13 divided by 15. Here the value is 0.12 and it goes on like that. You can see here in this table. That is the relative frequency of a class. Then cumulative frequency. Cumulative is simply adding up. Cumulative frequency. Cumulative frequency is the sum of the frequency for that class and the previous class. You go on adding up the frequency of one class with the previous class. Here the frequency is 6, 10 and 13 are the frequency. Then cumulative frequency. Cumulative frequency, here the first column, it is 6. Then next, cumulative frequency means 6 plus 10. 6 plus 10, the value is 16. Then next, cumulative frequency is 16 plus 13. That comes to 29. This is cumulative frequency. You have to add the frequency with the previous classes and it goes on like that. Now, expanded frequency distribution. In expanded frequency distribution, you have to find the midpoint of a class, the frequency of a class, relative frequency and a cumulative frequency. That is expanded frequency distribution, and in this table you can see here the expanded frequency distribution. Then with this table, how we are going to construct a frequency table? With this data, with this raw data of fecundity of insects, we are going to construct a frequency table. Here the lowest value is 2. First we have to find the lowest value. Lowest value is equal to 2 and the highest value is 80. Highest value is equal to 80. The difference between the highest and the lowest value, difference is equal to 80 minus 2, that comes to 78. Then with this we can assume how we can design the class interval or the width of the class. Width of the class, here we are going to take 10. Class width is equal to, class width is 10. Then number of class intervals. Number of class intervals is equal to the highest value, that is 80 divided by the class width. 80 divided by 10 is equal to 8. That is the number of class intervals with the width 10. Then class limit is the two numbers used to specify the limits of a class for the purpose of tallying the original observation into various classes. The lowest limit is the lower value and the upper limit is the highest value of each class interval. The class width is the range or length of a class interval or difference between the upper and the lower class limits. Class width is equal to upper class boundary minus lower class boundary, that we have explained before. Now we are going to construct a overlapping frequency table with this data. Overlapping and non-overlapping. First is overlapping frequency table, and in overlapping frequency table, continuous class intervals are used. There is no gaps between the class intervals. That is continuous. This is important. The overlapping frequency table is constructed by using continuous class intervals. This data here is a frequency of 45 insects. Continuous means first is class, then frequency, zero to 10, 10 to 20. The class width is 10 as I have said earlier. Then 20 to 30. This is continuous. Here the lower limit of the second class will be the upper limit of the first class. That is, this is continuous, means upper limit of the first class and the lower limit of the second class will be same. Then 20 to 30, 30 to 40, 40 to 50, 50 to 60, 60 to 70, and 70 to 80. 80 is the highest value which we have. And coming to the frequency of the variables which falls between 0 to 10 and less than 10, we have here two values. The frequency of the is 2 here. That is, the variables which comes between 0 and 10 is repeated twice, and between 0 to 10 we have the value 2. So 0 to 10 the frequency is 2. Then coming to the next class, that is 10 to 20. The values which comes between 10 to 20 we have to count, that is 4. Between 10 to 20 you have 4 values. 1, 2, 3 and 4. 4 values. And one thing which you have to note here is we have the value 20 here. In this raw data, the value 20 is there, but we won't include 20 in this place. We will be including 20 only here. Then the next 20 to 30. So 20 is taken into consideration here only. 20 to 30. That is because it is continuous and there should not be any repetition between the values. So in all cases, while we preparing overlapping frequency table, we will consider only the upper limit in the second position, that is here, from 20 to 30. Then from 20 to 30, the values here you can find 16 is there, 19 is there, 20 is there. It comes to 6 and it goes on like that. You can see here how it is prepared, the overlapping frequency table. Now next is non-overlapping frequency table. Non-overlapping frequency table is constructed with discontinuous class intervals. Discontinuous class intervals. And here the class intervals are frequency. The class intervals are 0 to 10. I said it is discontinuous. So the next class will be 11 to 20. That is the second class because it is discontinuous. And the next class it will be 21 to 30. The next is 31 to 40, 41 to 50, 51 to 60, 61 to 70, 71 to 80. That is the class interval. One thing you have to note here is it is discontinuous. Then in this 0 to 10 only 2 values. 2 is repeated twice. 0 to 10 the frequency is 2. In this case, we don't have any confusion of including either 10 here or here. It is clearly because 10 is coming here only. So, we have no confusion in this including the value 10 there. In this class interval 10 to 20, the total number are 1, then 2, 3, 4, 5, 6, 7, 8, 9 and 10. 11 to 20, 10. The frequency is 10 because here the value 20 is taken into consideration at this class interval. Then next, from 20 to 30 it is 6. From 31 to 40 it is 4. It goes on. You can see here the overlapping frequency table, and sigma f for the total frequency is 45. These are the non-overlap. This is a non-overlapping frequency table. In biostatistics, usually non-overlapping frequency tables are used. In this tutorial, we have discussed about the frequency table, how to construct a frequency table, and I thank you all for your kind listening.